Welcome to RF transceiver design course. We are discussing about low noise amplifier design, and in last class we have seen if S parameter is given to us, and based on the S parameter how we can proceed to design a low noise amplifier. So, in order to get the S parameter of the amplifier, you need to bias your transistor, and based on that you will get the S parameter. It is provided might be from the foundry or the device manufacturer, or you can also use a simulator to simulate the S parameter based on your design. It might consist a single transistor or more than one transistor or transistor network, but it will be represented as a 2 port, and you should know the prior S parameter of that for designing the low noise amplifier by using the S parameter. We have also seen the uh, how to make the noise circles, gain circles, and how we can identify the input reflection coefficient gamma s, by which you can make the input matching network such that you will get a low noise amplifier as per your desired noise figure. So, now we will specifically target the MOSFET because it is in RFIC, it is a widely used components, and how we will make a low noise amplifier design by using a MOSFET. So, let us discuss the noise in the MOSFET. So, if MOSFET, if we consider a 2-port noise parameter, so MOSFET is comprised of a 2 source. If we consider the thermal noise, then it has a drain current noise. So, one is a drain current noise and another is a gate current noise, because there is a gate current as well as a drain current, and gate current is happens because here we are considering a very high frequency, and when we consider the high frequency we cannot avoid the capacitance CGS. So, if you are working at low frequency, you can generally consider this as a open circuit, but at high frequency there is a, if this is a gate, if this is a source, and if this is a drain. So, Gm into VGS, and there is a RO. So, if we are working at high frequency, we cannot avoid this capacitor CGS, and while discussing the active components, we have also defined the FT and Fmax by using this CGS. So, that is why there is a gate current noise, and it is given by ING square. This is a mean square value of the noise current, and it is given by 4 kT gamma GG into delta F. We already have seen in the, while we discuss the noise, how this delta F is coming, that is a per unit bandwidth. So, we have defined the noise power is kTB, and we need to consider the bandwidth. Similarly, for the drain current IND, mean square current, noise current is given by 4 kT gamma GD naught into delta F. So, this is for the gate and this is for the drain. So, here Gg is given by omega square Cga square 5 into Gd naught. So, gate noise is correlated with the drain noise with a correlation coefficient C, that is Ing into Ind conjugate divided by whole square Ing square root of Ing square into Ind square mean square. So, if we consider the correlation, and if we find out that 2 fundamental MOSFET noise sources, if we back to the input port, we already have done this for while discussing the LNA design, and in that we have defined the input referred, means if we see the voltage and current at the input side, you can write it down a drain current noise back to the input as a noise voltage. So, In last class we have also seen that if we want to define the voltage and current at the input side, so here there is a current, that is voltage is defined as a En square, and similarly there is a current can be defined as a In1 square. This is a mean square. So, this we are considering at the input side, and if MOSFET is a two port network. In the previous example also, when we have calculated the noise figure, minimum noise figure, at that time also we have considered the input referred noise current and noise voltage. So, En square can be written as a Ind square by Gm square, because we are considering at the input side, and then you can write 4 kT gamma Gd naught delta F by Gm square. So, Rn, so capital Rn, that is defined in that noise figure equation, can be given by En square by 4 kT delta F. So, this is a voltage by current, we can get gamma Gd naught by Gm square. So, this is a resistance Rn. Now, noisy drain current also flows when the input is open circuit. So, this we are also considering the noisy drain current, that is In1 square mean square. So, Ind square into j omega Cgs by Gm square. So, we should consider the impedance j omega Cgs. So, here this is a this is given by Ind square, that is En square into Gm square. So, we can write Ind square En square into Gm square will be cancelled out. So, your In square is nothing but En square into j omega Cgs whole square. So, total input current noise is equal to reflected drain noise plus induced gate current noise. So, this is a total input current noise. So, induced gate noise current, it is correlated with the drain current noise and uncorrelated with the drain current noise. So, the way we have defined in the correlation admittance Yc, to find the correlation admittance Yc equal to In1 plus Ingc. So, this is a correlated drain current, and then this is a uncorrelated drain current. So, In1 plus Ingc by En will get j omega Cgs plus Ingc by n. So, finally, we get j omega Cgs plus Gm into Ingc by Ind. So, the Yc is equal to j omega Cgs plus Gm Ind conjugate by Ind whole square. So, that can be written as a j omega Cgs plus Gm, because this is the same as the correlation coefficient C, square root of Ing square by Ind square. Now, we add both Ing and Ind from the previous equation, that is Ing and Ind. So, this is Ind and Ing, one is a 4 kT gamma Gd naught delta F, and Ing 4 kT gamma Gg delta F, and where Gg can be considered as this term. So, we will get the Yc in terms of delta j omega Cgs Gm by Gd naught correlation coefficient delta by 5 gamma omega into Cgs. So, this is both are the process dependent parameter delta and gamma. So, we can get the Yc, which is j omega Cgs 1 minus alpha into C square root of delta by 5 gamma. So, this term Yc is depend upon Cgs, the alpha, then correlation coefficient C delta by 5 gamma. So, here alpha is equal to Gm by Gd naught, and the parameter alpha exhibits value of 1 for long channel device. So, mostly for long channel device it will be 1, whereas it gradually diminishes as the channel size decreases. So, Here we get all the parameter gt which is 0, bt which is this value, that is uh, bt omega cgs into 1 minus alpha omega cgs 1 minus alpha c square root of delta by phi gamma. Rn we have already find out the value of Rn, and then Gu can be given by this equation. So, we got all Gt, Bt, Rn and Gu, then we will try to get the G optimum based on the Gu. So, G optimum is given by square root Gu by Rn plus Gc square. So, if you try to keep value of Gu and Gc, so we have already defined this equation in the previous slides for how to get the F mean equal to alpha omega cgs delta by phi gamma 1 minus c square. So, here if we want to find the F mean, which is equal to 1 plus 2 Rn G opt plus Gc equal to 1 plus Rn, means you can replace the value of Rn, and G opt and Gc, you will get the final value in this term. So, now for different value of omega by omega t, so here omega by omega t is a 20, you will get F mean which is equal to 0.5. Now, for in order to find the F mean, here gamma is considered a 2, delta is equal to 4, and the based on the value of omega by omega t, we will get the for omega by omega t of value of 20, we will get F mean which is 0.5, and C is a correlation coefficient. So, how much correlation is there between I and means gate and drain current, noise current, that is given by the correlation coefficient C. So, based on the value of omega by omega t, you will get the F mean. So, here the things that we need to observe, that as your noise minimum noise figure F mean is inversely proportional to omega t. So, while designing the low noise amplifier, if you are targeting high frequency, then your omega t, if you want to have a low noise figure for higher frequencies, you need to have a higher omega t. So, your device should have a, it means you need to use a very fast device where your Ft is higher. So, Ft and omega t both should be high in order to get the minimum noise figure. So, here while considering the minimum noise figure, we have only calculated the based on the source impedance. Now, if there is a source impedance is matched with the optimized impedance. Now, if we want to consider the power match, so there are two things, one is the impedance match and another is the power match. So, in low noise amplifier design, we should consider both impedance and power match. How can we try to optimize the power and have a better impedance matching? So, noise optimization with a power constraint, we already have find out the equation of noise figure, which is F mean plus Rn by Gs, Gs minus G opt square plus Bs minus B opt square. So, here if we assume Bs is equal to B opt, if the source susceptance, means if we consider the Y, so Ys is equal to, if we want to have a conjugate match with the Y optimization, so we should have a Bs is equal to minus Bs is equal to B opt. So, your F is equal to F mean can directly be written as a F is equal to F mean plus Rn by Gs, Gs minus G opt. So, your G opt here can be rearranged in terms of quality factor. So, quality factor Q is given by imaginary part. So, Q opt which is equal to G opt by omega CGS. So, here this is a real part. So, we already have defined that Q is nothing but imaginary part of y by real part of y. So, here imaginary part is nothing but a G opt and real part is given by the omega into CGS. So, Q opt is given by alpha square root of delta phi gamma. So, if we try to replace the G opt from this equation, if we try to replace the G opt from this equation, we will get the Q opt which is C opt by omega CGS alpha square root of delta phi gamma 1 minus C square, and Qs is given by for source side 1 by omega CGS into Rs. So, because there is a series, there is a capacitance here, Q is considered as a 1 by omega CGS into Rs. So, your quality factor Q opt and Qs, if we try to replace this in this equation, Gs and G opt, we will get a noise figure in terms of Q opt and Qs. So, F is equal to F mean plus gamma by alpha Gm into Rs. So, that is what we have done. We have replaced Rn and Gs gamma by alpha Gm into Rs 1 minus Q out by Qs whole square. Now, we already know the drain equation. Drain current equation is given by the complete drain equation is given by this mu n Cox W by L by 2 Vgs minus Vt, and here Vgs minus Vt is in relation with the electric field in saturation, and L is the length of MOSFET. So, ID we can rewrite as a WL Cox V saturation, then E saturation, and there is another term rho which is depend upon overdrive voltage which is Vgs minus Vt by L into E saturation. So, this is the another way of writing the ID equation. Now, we will find the power dissipation, that is the PD which is equal to VDD into ID. So, your PD is given by VDD WL Cox V saturation into E saturation rho square by 1 plus rho square, and your Gm is equal to alpha GD naught. Now, what we want is a minimize this power dissipation. So, how can we minimize the power dissipation? If we try to find out the value, means if we want to minimize, we need to minimize with respect to the value of rho, and if we try to work for this, we will get the optimized width for which we will get the minimum power, and that is given by the 3 by 2 1 by WL Cox into Rs. So, this will provide us the optimum width for power consideration. Now, when you try to use the optimum width for power consideration, your F mean is can be re-derived, and it can be mentioned, it has a 2 term 2 by 2.4 gamma into alpha omega by omega t, and here the F mean that we have derived in the previous slides. So, that is 1.1 plus 2.3 omega by omega t. So, here again your F mean is inversely proportional to omega t. However, if let us say you have omega t by omega is equal to t 20, if your omega t by omega is equal to 20, if you consider gamma is equal to 2, delta is equal to 4 and alpha is equal to 0.85, then you will get a F mean which is equal to 0.5 dB F mean power is equal to 1.1 dB. So, this is considering only the source matching. So, and this is considering, means this is considering only the impedance matching, and this is considering by power match. So, when there is a power and impedance both is matched, at that time your noise figure is increased by around 0.5 to 0.6 dB. So, for omega t by omega, if it is 15, it is increased to 0.6 and 1.4. If omega t by omega is 10, it is 0.9 and it is increased to 1.9. And here if omega t by omega is 5, then your noise figure is 1.6 in this case and 3.3 in this case. If you consider the omega optimum p, this value, this is a power minimum noise figure that you will achieve. So, what it says, for the MOSFET, if you want to design a low noise amplifier and if your omega t by omega is equal to 20, that means if it is omega t, if it is 200 gigahertz and if omega is a 10 gigahertz, then you will get a 20. So, if you are designing a low noise amplifier in the technology which is providing you the Ft of 200 omega t of 200 gigahertz and your omega is if your desired omega is 10. So, if your Ft is 200 gigahertz and your desired frequency f naught. So, omega t by omega we can also write Ft by f, both are same because 2 pi will be cancelled out. So, Ft by f which is equal to 200 by 10. So, at desired frequency of 10, you will get a minimum noise figure 0.5 dB. So, you cannot get less than this noise figure. If you consider the power match, then your noise figure is 1.1 dB. So, this is how, means you will get a 10 gigahertz. Now, if you try to increase the frequency, your omega t by omega is means omega t by omega is reducing, and that will increase the noise figure. So, this is what is a power match and the impedance match constraint, and while calculating this chart, the gamma is considered as a 2, delta is a 4 and alpha is a 0.85. So, this is what is the impedance match and power match. So, the I think this is about the MOSFET noise. Now, we will try to consider the various topology of the low noise amplifier and how that various topology we can design. So, we have already discussed while discussing the receiver architecture that your noise figure f is equal to SNR in by SNR out, and it is given by 10. So, this is a noise factor f and noise figure is 10 log into f. Your gain, voltage gain is given by this, that is a 20 log of V out by V in, and we already have seen the Friese formula that your first component in the receiver will identify the noise figure of the complete receiver chain, because if we see the Friese formula, the first term is f1 plus f2 minus 1 by the gain of the first stage. So, the gain of the low noise amplifier should be high and the noise figure should be less in order to minimize the noise figure of the complete receiver. So, this is by this way we can able to get the minimum noise in our receiver design. So, that is why low noise amplifier is important in the transceiver design, and we are going to see the many different kind of topologies for designing the low noise amplifier. So, linearity also we have already seen. In linearity, if you want to achieve the we have discussed the two kinds of linearity. One is a intercept input intercept point. We have also discussed the IIP2 while discussing the receiver architecture. So, both linearity is also important when we are designing the low noise amplifier, and stability also we have discussed. So, if we want to design a LNA design requirement, it should have a broadband input matching to minimize the return loss. It should have a sufficient gain to suppress the noise of the mixer, and low noise speaker to enhance the receiver sensitivity, and low power consumption to increase the battery life, and small die area to reduce the cost. So, this is very important for designing the low noise amplifier. We have already discussed one of the way, if S parameter is given to us, how to find the how to design the low noise amplifier. Now, we will try to design the low noise amplifier by using the circuit methodology, where we try to see the we will try to discuss the step by step, what is the input impedance, what is output impedance, how we can calculate the noise, and what is a gain. So, this is about the low noise amplifier. Thank you. We will discuss more in detail about the all topology of low noise amplifier.